Hi. Thalidomide was a drug which was prescribed to pregnant ladies for sedation. Now it did its job, but along with it, it gave birth defect to kids born around the world. Now, this was a grave situation. You take a drug for sedation, but it defects kids' genes in such a way that the entire life of that kid is ruined. Obviously, it created much hue and cry around the world. Now, scientists, physicists, chemists were all wondering how come the product being so pure creates such a chaos. Meanwhile, somewhere around the world, a new type of compound was explored, and it was called as chiral compound. Now, thalidomide belonged to this category. So the entire world now diverted towards chiral compound. What were those compounds? How do they behave to our biological system? How is their interaction with our biological system? Was the entire curiosity. And what is there in it that, in spite of being absolutely pure, synthetically pure, it creates such chaos? This is Dr. Ankur and his esteemed colleagues who are going to try their level best to make you understand the gravity of situation. And it's our job actually to make you aware about these chiral compounds, mysteries of these chiral compounds. How fatal could it be? Okay, I hope you enjoy the video. Hi guys, I'm back. We are talking about chiral compounds. To begin with, let's understand this structure that I've drawn over here. It's a carbon compound. Now, carbon is a tetravalent compound. It has got 4 bonds, all right, and 4 bonds. But we are talking about chiral compound. So, how is it different than normal compound? In case of chiral compound, we would observe that all 4 groups which are attached has to be different. That's what we are finding over here. This is ethyl group, this is methyl group, this is hydroxy group, and this is hydrogen. Just to generalize, we have designated here as A, B, C, D. So come back here, you see here carbon with A, B, C, D, 4 different groups attached. So that's the criteria which is required for a compound to be chiral, and we designate it by asterisks. Right. So now that's not the only criteria which is required for a compound to be chiral. Now, suppose if I bring this compound in front of a mirror, now this is the mirror and this is its reflection. What do we find? We find that it looks identical, just like in Hindi movies we see Ram or Shyam, where Ram and Shyam, they are all same, but there is some difference in them. Now, what's that difference? But we know when it is in movie, it is the same person who's acting. So it's the same, but here it is not the same. If we just pick this up and try to overlap over this, definitely it won't be. It appears to be, but it won't. Why? Because CH3 would be overlapping with this, H over this, whereas these are okay. These would be overlapping. But again, if you see this structure also, there also. So in short, this is not superimposable over its image. Okay, so this is the second requirement that we need for a compound to be chiral. All right. So for a compound to be chiral, what are the two things which are required? First thing is 4 groups attached has to be different, and they are supposed to be not superimposable. All right. Okay. Now let us. I hope the camera covers up this. Now let us understand. Now how do we differentiate them? I told Ram and Sham. So how do we differentiate Ram and Sham? Now this is how we differentiate. If I call this as plus, I have got to call this as minus. If I call this as D, now one thing I need to clarify over here. If it is minus, then we call it as L, levorotatory. And if it is plus, we call it as dextrorotatory. Now this part would be covered very nicely by Mrudula, our colleague. Okay, and then comes also R and S. This is an absolute configuration, and then also comes D and L. Now I am not covering up these things because right now we are not very keen into understanding these. These things would help us understanding it better. Fine. So that's about this. Now, so what is the significance? What is so great about these chiral compounds? Now, if I want to synthesize chiral compound, now these I'm just sorry I didn't mention you that these are called as enantiomers or optical isomers. This is positive enantiomer. This is negative enantiomer. This is positive optical isomer. This is negative optical isomer. Correct? So these are isomers. Now, what is so great about it? Synthesis. Now, we are talking about synthesis. Now, if I want to synthesize only one of this, then I have got to use chiral catalysis. This chiral catalysis part would be covered by Sarvadnya and Srushti. Sarvadnya and Srushti would be covering up this part nicely. Okay, so I'm not going into detail. So you require chiral catalysis. Now, if we don't use chiral catalysis, if we use achiral catalysis, then what happens? We end up with Ram and Sham. So twins are born. Now what are those twins? Now we will have, if we are not using chiral catalysis for synthesis of this compound, then along with this, even this would be formed, and it would be in mixture of 50-50, which we call as racemic mixture. So we are going to deal about these racemic mixtures and chiral compounds in our future videos. I hope it's all clear till here, and you would be enjoying viewing further.
Let us start with some properties of optical isomers. Hi, this is Rachana. When we talk about optical isomers, the first thing that comes to our mind are two compounds having the similar molecular formula, and as we said earlier, they are non-superimposable. Here are some of the pharmaceutical drugs and some flavors and fragrances. To start with pharmaceutical drugs, the first one over here is thalidomide. Here, the positive optical isomer acts as a sedative and the negative optical isomer acts as a teratogenic or as a birth effect. The next one is propranolol. Here, the negative isomer acts as a beta blocker of the heart and the positive isomer affects fertility. The last one of the pharmaceutical drugs is ibuprofen. Here, the positive optical isomer acts as a pain reliever or anti-inflammatory, and the negative optical isomer may possess many side effects. Unfortunately, as we know that every coin has its two sides, here for the desired as well as the undesired elements of the coin. From this we can conclude that even a small change in the spatial arrangement of these optical isomers can make a huge impact in the life of our human beings. Let's get to some enjoyable part. Here is limonene. We all must have experienced the fragrance of orange and lemon, but do we know the difference between them? Here, let us see. The positive optical isomer gives us orange fragrance and the negative optical isomer gives us lemon fragrance. Isn't that interesting? The last one is caravan. Here, the positive optical isomer gives us caraway or ajwain smell and the negative optical isomer gives us mint fragrance.
Hello, myself Anmol. As my colleague Rachana already explained some facts about optical isomers, in continuation with that, we can see the enantiomers in green possess desired activities while the enantiomers in red possess undesired activities. In spite of having identical molecular formula, they possess different activities. Like, why is it so? Can you guess why is our body so enantioselective? It is because Our body is made up of many chiral molecules. Cell walls, enzymes, sugars, proteins, DNA, RNA, etc. are present in our body are made up of single optical isomer. Hence our body is so enantioselective. Just like a specific key fitting a specific lock. The key which fits in the lock represents desired enantiomers, while the key which doesn't fit in the lock represents undesired isomers. As a result, our body responds differently towards positive and negative optical isomers, as seen in three pharmaceuticals presented before. Highlighting the part of undesired optical isomers, if any undesired optical isomers remain inactive in our body, the question arises, what does it do to our other biological system over an entire period of time? It's still unknown. As we can see in the case of ibuprofen, its negative optical isomer may possess many side effects and sometimes even fatal. Guys, don't you think there's need for awareness?
Hi friends, this is Mrudula. Previously, we have already studied what are optical isomers and their biological effect on the body. Continuing with the topic, the two types of enantiomers are identified using a polarimeter. Now, what are enantiomers? Enantiomer is a single optical isomer. A polarimeter consists of a light source, a polarizer, a polarimeter tube, and an eyepiece. The light source consists of unpolarized light having vibrations in all directions. As the light passes through the polarizer, it vibrates along the plane of the polarizer. Hence, it is called as plane polarized light. On the other hand, in circularly polarized light, light vibrates in two planes perpendicular to each other. So let me just read this out for you. In circularly polarized light, light is made up of two plane waves of identical amplitude varying by a phase of 90 degrees. As the light passes through the polarimeter tube, the observer will observe a band of light on the eyepiece. So on introducing one of the enantiomer of a racemic mixture, the band of light is observed to be rotated on the left hand side of the observer, say by 30 degrees. Since it is rotated on the left hand side of the observer, we call it as levorotatory. It is designated by a negative sign, so the rotation would be negative 30 degrees. On introducing the other enantiomer of the same racemic mixture, what do we expect? Since it is the enantiomer of the same racemic mixture, it would be plus and 30 degrees, so we call it as dextrorotatory. Now, a racemic mixture consists of 50% composition of levorotatory and 50% of dextrorotatory. So what do we expect? Obviously, the minus 30 degree of levorotatory will neutralize the plus 30 degree of dextrorotatory. So the net rotation would be 0 degree.
Hello everyone, this is Shravani. My colleague Mrudula has explained the concept of polarimeter. Now we would be understanding some synthetic techniques for synthesis of single optical isomers as well as methods for resolution of racemic mixtures. Here are some methodologies mentioned like mechanical separation, enantioselective photodestruction, stereoselective complexation, chemitransformation, and kinetic resolution. Me and my colleagues would make you all understand these methodologies in detail. So firstly, let us begin with the primitive or an old methodology called as mechanical separation. In this separation, we can find that the enantiomers have different lattice structures, due to which we can pick them up easily by tweezers. This methodology can also be carried out by formation of diastereomeric compounds with an optically pure reagent. For example, we can see a racemic mixture A with a positive as well as a negative enantiomer and an optically pure reagent B. They both react with each other to give two diastereomeric compounds. We can see that the positive B gets combined with the positive of A to give positive A and positive B diastereomers. Similarly, the positive B gets combined with the negative of A to give negative A and positive B diastereomer. As we get two diastereomeric compounds, it was expected to have different properties. Therefore, it was observed that they have different boiling points and different solubilities via crystallization, due to which these were separated from each other. These are also separated from each other due to differences in the absorption coefficient. Hereby, we can conclude by saying that these diastereomers have different properties due to which they were easily separated from each other.
Hello friends, this is Sarthak. We'll be understanding some techniques used to synthesize desired enantiomers. Firstly, we'll start off with enantioselective photodestruction. Here we have a plus minus A racemic mixture. When h nu, which is a energy in the form of light, which is a circularly polarized light, when one of the isomer of the racemic mixture is eradicated by the h nu, we get two isomers, that is, one is unaffected and the other one gets decomposed. Therefore, we are only left with minus A. Secondly, we start off with stereoselective complexation. Here also we have a racemic mixture plus minus A. It is reacted with metal with optically active ligand, where M is the metal and B is the chiral ligand. After that, the metal with optically active ligand forms enantioselectively forms a complex with the positive isomer of the racemic mixture, and the negative isomer remains unaffected. So, to be precise, here we are separating the optical isomers rather than synthesizing them.
Thanks, Sarthak. Hey there, this is Sarvadnya, and now we will be focusing in depth about chemitransformation and kinetic resolution, which have been currently used for synthesis of desired enantiomers. Firstly, starting with chemitransformation. What is chemitransformation? The word itself depicts that here we would be dealing with pure chemicals. Starting with the reaction process, firstly we would be taking a pro-chiral compound which on reaction in presence of chiral catalyst gives one of the enantiomers as the product. Talking about kinetic resolution, here we would be dealing with biotransformation, in which we would be using biocatalysts as enzymes. Talking about the reaction, we would be taking plus minus racemic mixture of A, which on enantioselective reaction with non-chiral compound B gives this product, while the positive enantiomer of the racemic mixture remains unreacted. Now my colleague Srushti wants to interrupt me for a while. Let's see what she intends to say, and then I would be back.
Thank you for your invitation, Sarvadnya. I'm Srushti, and I'm going to explain some scientific contribution of Ankur and his colleagues in the field of chemoenzymatic kinetic resolution processes. He explored resolution of practolol published in biotechnology letters, propranolol published in Journal of Organic Chemistry, atenolol published in Journal of Organic Chemistry, which were beta blockers, hard drugs. Ibuprofen published in Indian Academic Society, which was anti-inflammatory. He also put an effort into a novel method of synthesis of amino acids, so for which racemic mixture of oxazolone was used and kinetic resolution process was performed. Racemic mixture of oxazolone opens up by a chemoenzymatic kinetic resolution process to form plus enantiomer of amino acid and minus enantiomer of oxazolone remains unreacted, or minus enantiomer of amino acid and plus enantiomer of oxazolone remains unreacted. The unreacted enantiomer of oxazolone auto-racemize, that is, if minus is there, it will turn into plus minus. So racemized mixture of oxazolone is again created. The reaction continues till maximum yield is formed. As we have seen earlier, in case of kinetic resolution, the yield form is 50%. But in this particular reaction, even though it's kinetic resolution, the yield form is much more than 50%, it's nearly 90%. Why? Because of auto-racemization. So it's a novel process which competes with asymmetric synthesis, which will be explained by my colleague Sarvadnya later. So, my dear colleague Sarvadnya, this wasn't an interruption but a very valid information. Okay, got it?
From racemic mixture, the 50% of the racemic mixture reacts to form this product, while the other 50% remains unreacted. So the expected yield here is approximately 50%. In chemitransformation, we would be dealing with a pro-chiral substrate which on reaction in presence of chiral catalyst gives either positive or the negative enantiomer, which is chiral. Why this is chiral? Because the central carbon atom here has 4 different groups attached to it, while here we do not see any such chirality, but this on reaction gives a chiral compound, hence this is termed as a pro-chiral compound. As we saw here that we are getting 100% yield of any one of the enantiomer. On the other hand, here we were only getting 50% yield of the enantiomer, it can be said that chemi-transformation is more preferable than kinetic resolution.
All of this work presented by Srushti, courtesy Google. For further details, you can please visit Google.
Guys, at the end, what we conclude is chirality has been existing around us in fact, I would say not even around us, prior to us, since it has been existing for last 2.4 billion years in cyanobacteria as enzymes. Now, cyanobacteria is a gram-positive bacteria and supposed to exist for nearly 2.4 billion years. And today, we have drugs. Majority of our drugs, chiral drugs, are racemic mixture. Isn't it very upsetting that this subject, though we are aware, as I myself in the beginning of our video confessed that it was during 1960s that chirality came into our existence. Alright, but still, don't you think it's now high time that we try to find out most of the drugs, chiral drugs, which are sold as racemic mixture, try to find out methodologies to resolve these optical isomers, and not only resolve but also to find out actual biological interactions of each of the isomer, positive and negative. What biological interaction does it have? Negative isomer, what biological interaction does it have? So it's high time. Unfortunately, what's happening is we are starting with either resolution or synthesizing optically pure molecules, but it all ends up into fundamental research. But hardly any process goes into commercialization. Now we have seriously got to think of getting this projects commercialized, or rather see to it that instead of getting fundamental research, publications and all those things on our name, let's do something for the world and try to see that at least few, if we take a mission of few chiral compounds, we see to it that at least some of them we take it to the process of commercialization. I've been very rude probably. I myself have worked onto these projects. But then it's high time that we move ahead and think about commercialization of most of these processes and get many of these chiral compounds in their optical purity. This would be a great contribution towards the world. And then we would be living in the world, in a happy world where we won't have any fear, apprehension about these drugs, because we would be having most of the drugs are racemic mixture. We would be having most of the drugs in their optical pure form or enantiomers, and we would be aware about what enantiomer does what to our biological system. And don't you think that would be a happier place to live? I hope we all work towards it and get more of optically pure compounds. Whichever method, kinetic resolution or asymmetric synthesis, or whichever way, about what enantiomer does what to our biological system. And don't you think that would be a happier place to live? I hope we all work towards it and get more of optically pure compounds. Whichever method, kinetic resolution or asymmetric synthesis or whichever way, but please let's get into it. Alright, so maybe when we speak next, it should be most of the pharmaceutical chiral drugs are sold in enantiomers. But right now the statement is, even today, most of the chiral drugs sold are racemic mixtures. Okay, with this note, wishing you goodbye for now. See you soon.
Thank you. Hope you all enjoyed. See you soon.